So the identity type over A, we wrote M and N, which you'll recall represented the type of proofs that M and N are equal. So we're looking at two possible interpretations of IDA MN, which kind of in the end amount to the same thing. But what the idea is that it's the type of proofs of equality of some form, and that's what we're going to discuss in a minute. The other way to think of it is that it's the path space, it's the loop space, it's the type of paths between M and N within A. And the remarkable thing is that these are just, it's a matter of how you cock your head. They're the same thing, and if you like to think in terms of paths, if you like to think in terms of proofs, it's all the same idea. Okay? And that's the kind of interesting fact, is that, so it's another example of the idea that, you find, it's an indication of the depth of the ideas because they have the same concepts manifest themselves in superficially distinct ways turn out to be the same. So, okay, so what we were doing is we were looking at this, and we were observing, what?
Try to orient myself here. Last night when I was thinking about this, I kept feeling that there was a difference without a distinction here. That the type of proofs of equality of M and N, the way you defined it, is only actually inhabited by reflexivity.
Well, wait, I'm working on it. Okay, we're going to see. Let me get there.
Okay, so 1 and 2 at the moment.
Yeah, but this is like the conceptual thing. What is the point of the identity type? I didn't really say so. I said right from my first lecture, there's an issue about exactly what I mean by equality. So that's my main version.
So the present definition is not the final one.
Say again?
The present definition.
The present definition. Yeah, well then it's we're I'm going to say it's going to let me continue. I'm going to ask you. Okay, was there other questions? Okay, so what we did is we gave a proof that, of course, it's reflexive. Okay, so that's by definition. Okay, we gave a proof that it's symmetric, and I asked you to do the proof that it's transitive, and completely predictably, it was kind of a nasty question. I didn't really expect anyone to figure that out. It's actually rather hard. Did anyone actually figure that out? You did. Oh, good for you. All right. Well, if you did, you're in a distinct minority. It looks like 2 people or so figured it out. So what I was telling you is you have to look at the motive. And the motive to consider, I don't actually need the Z, looks like this. What you do is, well, it's going to amount to sort of a trick. It says that you prove that if V is equal to P, then U is equal to P. I don't really need the W or Z or whatever here. I don't actually use it. So I'm only interested in that. So this is the motive. Okay? All right? You prove this. And so now you should be able to do it. Okay? If you use that as your motive, you need 1 instance of J. And remember, the conclusion will be you're going to plug in M and N. So when you plug in M and N, you're going to use that as the motive. And remember, we have assumptions. A is something like M and N, and Y is id A, N, and P. And we want to show something is id A, M, and P. Okay? So the way we're going to do this is, because of the way we chose the motive, what we're going to get by a use of J on X with something will end up being anything if it'll end up saying if N is equal to P. Is that what I want to say? No, if M and N, yeah, I want to say if N is equal to P, then M is equal to P. Yes, good. Because I'm going to plug in M and N for U and V, and they're going to get swapped, so it'll be N to M. And it'll look like this, and this is one of your assumptions. So you'll end up taking that J and apply it to Y, and you'll be done. So now all you have to do is fill that in. Okay, that's a trick. So that's how it is done. That's how you can prove transitivity. And by a similar argument, you can prove an important property, and I'm going to give you another exercise called substitutivity. So substitutivity. And this is something which is, it's usually called substitutivity, you could say, or functionality. And it looks like this. The best way to write it out is to say the following rule is derived. Let me write this down. So it says, if I have an A-indexed family of types B, and I have a proof P that M and N are equal, where the assumption would be that these are both of type A, okay? And I have, what did I call it here? Let me just check. Yep. And I have a Q, which is M for XB. Then I can transport. So this is sometimes called, and this is sometimes called transport. And maybe there are other words as well. That what you do is you then say, I can do an operation which I will call subs PQ, which is going to be defined. Okay, I will define this. Okay, whose type is N for XB. Okay, and that's expressing functionality. This is telling us that when thought of as a mapping, this family of types respects equality. Because if you give me something in M for XB, and M is equal to N, then I can turn that into something of type N for XB by transporting it along the proof that they're equal. Okay? So this is where the terminology of paths feels good, okay? Because I'm transporting along that edge, the edge that connects right here, this path P, which connects M and N. Okay? So you can think of M and N as being connected by some sort of path. And then if you look at the fiber over M in this dependent type, then it means we have a B over M here, and we can transport it. So we have the B over M here, essentially, which comes down here. And we're going to then, there's something called the lifting property, which lifts this path up to this space in such a way that it lives over here. And that, in fact, is an instance of what is called the homotopy lifting property, and becomes the definition when worked out of what is a fibration, and Steve will show you that. Okay? So this is what is going to be happening. So we'll be able to show you how to do this. So this picture is, we're going to define how this is done. And again, the same thing is to get, you get the motive. And the motive is, you take as your motive U, V, and I don't care, and it's dot, and then it's a function, well, yeah, the function which is, excuse me, I think it is U for XB, arrow V for XB, which sort of makes sense now, particularly if you saw that example. Because what I'm going to do now is I'm going to create a function that goes from the U instance of B to the V instance of B. By a J limb, those will become M and N. So then I will say, take something in M and turn it into something in N, and then I will apply it to the something I have in M, and I will get back something in N, which is what I require. So this is the motive. And so from there, you can do the exercise. Okay? All right, so I will leave you to finish that. So finish the proof. And then there's a closely related property called respect, which I would like to do as well, which says that the same thing happens with families of terms. And I can write this over here. So it says, if I have a family of terms in a family of types M, like that, it's nice for me to, let me try to keep my notation straight. That's why I keep referring here. So I want to do this, okay, and then what I do is I say, well, if I have P, this is one form of respect anyway, M and N. So I want to say that Q should be thought of as a mapping in the sense that it's going to respect equality in this position. And so what you do is you will be able to define an operation called resp QP. And what that will do is it'll be a proof that id be M for X. So I'll do a fixed B. You can also do this more generally, but I'll do it for a fixed B. M for X Q is equal to N for X Q in B. Okay? So this is telling us that the open term Q is functional in the free variable x, because the m instance and the n instance are going to be equal. In a minute, before very long, I will have introduced the idea of a Grothendieck universe. And then what will happen is there's a similar principle of respect which applies to types, because this will be some universe of types here. B will be a universe of types. And then we'll end up being able to say, as a consequence of respect, that in this scenario, the family of types m for x, b is the same as the family of types n for x, b, or is equal. There's a path between them. We'll get to that in a minute. That involves universes. But right now, let us just leave those as two. And this I'll leave as an exercise. Given all the other hints I've given you, you should be able to do that one. Okay? So those are good. So now we get the beginning structure, okay, of what is happening with the identity type. So these are things that are like going on, so to speak, for free, if you would like to say that. In other words, it's built into the structure of type theory in the sense that all I did was define things to be reflexive, and then these things were derivable. Okay? So these work for generic reasons. That's the thing I want to say here, right? They're not axiomatized. I don't postulate them. They're theorems, okay? All of these things, symmetry, transitivity, functionality, or whatever you'd like to call it, transport, et cetera, respect, those are all theorems, okay? So that's important, because it's going to tell us something. We're going to exploit that by when we alter the definition of what identity is, and that's what is going to happen here. Because the reasoning I did, all I cared about in all of these arguments, if you unravel everything, all I care about is that the elim form J is valid, okay? That you can proceed by using J, okay? So that's the, that's the idea. Okay, so now I would like to, I want to claim a theorem, and this is related to Bentley's question. So are we okay with this right now? Okay. I want to claim a theorem and then point out a very curious and unpleasant situation we are in. Okay? So let's explain that. So here's a theorem which I'm just going to claim. It was proved by Martin-Löf in 1973 in a very close form to this, and it's the same, which says the following thing. It says, if you have a closed proof of identity of m and n, of 2m and n, which are closed terms. So everything is closed. There are no variables. So everything is closed. So I have no assumptions. So I have a closed proof of equivalence at some type, closed type A, of closed elements m and n. Then they're definitionally equal. Okay, so that's the this can be proved by a rather involved meta theorem. And in previous instances of the summer school, I've spent 3 lectures, maybe more, developing the machinery required to do this kind of a proof. I'm not going to do this here. I've spent my whole time in previous summer schools on that kind of an argument, so I'm not going to do this here. But this can be proved by a logical relations argument, and Amal, when she's here, I think we'll be talking about some of that. And maybe you can then pick up the thread from there. So I'm not going to even say anything more than that. It can be proved. So what this is telling us is that the identity type, as defined the way I defined it, so the corollary is the identity type internalizes definitional equality. Okay, so that's what this is saying. That what I've actually captured in the way in which I've axiomatized the identity type is definitional equality. What I'm now going to discuss is a number of alternative ways to talk about the identity type that makes it richer. Okay? And this is what I am going to do. So let's first talk about why we would be concerned about this. Well, first of all, let me put the following problem to you. Okay, given everything we've done, so this is just a fact. Okay, I'm going to use this fact to make the following observation about a curious state of affairs. Okay, so the curious state of affairs is this. You can find a proof term P, going back to my motivating example a long time ago. You can find a P, okay, there is a P, such that, okay, P is a proof that x plus y is y plus x in N. You can find that proof P. What is that proof object going to look like? It's going to be a recursor, right, which is the thing we talked about last time. You're going to prove this by mathematical induction. You're going to do a double induction on x and y. Just imagine you were doing it on paper, right? You would have to work out, you'd say, well, if x is 0, then subcase y is 0. Well, the sum of x of 0 and 0 and 0 and 0 is 0 and 0, so we have no problem, et cetera. Inductive step for y, inductive step for x, okay? You could do it. That can be written down as a proof term. That's the whole point of type theory, is that that doubly inductive argument, which you would scratch out on a piece of paper, is a term, okay? So this is a recursor. So it's going to be rec x something, and I don't know, there might be various optimized versions of this proof I don't actually remember, but probably there's a rec y here. I don't actually remember. And then there's another case here, and there might be a rec y here as well. You know, it looks something approximately like this, right? Because it's a double induction, okay? All right. Say again, please. What is the... What does internalize mean? Oh, it means that you have the judgment of definitional equivalence. This is a judgment. This is, in some sense, the fundamental assertions of the theory. I'm internalizing it as a type whose proofs represent the fact that these two things are, as it turns out, definitionally equal. So what I was saying is when I define the identity type, in order to help you along, the first thing I said to you is, let's just pretend I define this crazy family of types by this particular arbitrary rule. Now I'm characterizing for you what I did. Okay? It ends up being the smoothest way to explain everything. Okay? So that crazy type constructor which I gave you, which was motivated by an inductive definition where you just have reflexivity, and then the elim was just motivated by what would induction over that mean. Okay? The upshot of that is I've internalized definitional equality as a type, or you could say as a proposition. Propositions are types. Okay? So that's the idea. That's a terminology people use. Say it.
Means makes it part of the type system.
Yeah. There's terminology you'll see in other places, like the notion of an internal Hom or things like this, and that's where this terminology fits into that kind of general framework. Okay. So yeah. So that's what I want to say, right? So like in the category of abelian groups, the homomorphisms, the group homomorphisms form an abelian group. So that means the category of abelian groups internalizes its own Hom, its own mappings, okay? Whereas for non-abelian groups, that isn't necessarily the case. I mean, so that's an example. I mean, there's this idea that it's not necessarily the case that the collection of maps, you can think of these as paths or maps from M to N. Think of these paths as also mappings from M to N, that transport M to N. It's not necessarily, so this should be thought of as sort of Hom sub A Mn. Okay, that's the way to think about this. And it's not necessarily the case that the collection of mappings between two structures is again an example of one of those structures. Okay, it doesn't have to be. If you're just working with general groups, the morphisms between groups do not form a group. Under additional assumptions, they do, like abelian groups do, or if you considered only the isomorphisms, then you would again have a group structure, but it depends on what you're doing. Okay, so it's not like somehow immediate. It's not obvious that you ought to be able to internalize the Hom, but I am here. I'm internalizing the Hom. Yeah.
And do you have the other direction of that application?
What's that again?
And N are definitionally equal, then it.
Yeah, that's immediate because.
Okay.
Because it's a derived rule, right? You'll be able to yes, you will be able to definitionally equal things will give you the same classifier. The reason is that this is a family of types, and family of types respect definitional equality. So id AMN is the same type as id AMM, and that's inhabited by reflexivity, and definitionally equal types classify the same terms. So you'll be able to conclude that under this assumption, if M is definitionally equal to N, then REFL of, well, whichever one you prefer, M or N, is an element of the type id A, M, N. And why is that? because this type is definitionally equal by congruence to id A and this is in here, and definitionally equal terms classify the same elements. So that's for free. Okay, so that's for free. So there is a subtlety. Like one of the big lessons we learned of type theory that is extremely hard to convey to someone who hasn't lived with the subject as you are doing, is just the idea of distinguishing judgments and types. In conventional logic, if you look in textbook logic, they don't distinguish the formula and the assertion that a formula is true. They don't have the idea of a judgment, and that is missing. And if you introduce the idea of a judgment, do that properly, and it's very hard for me I can say it, but really you just have to live it so that you can understand the force of what I'm saying. That in itself gives you a tremendous amount of freedom. So like Frank was showing you how to do modal logic with a validity judgment. It's extremely important that you had two judgments, truth and validity. Okay? It's very important. If you look in textbook logic, textbook treatment of modal logic, they don't have the concept of judgment. Therefore, they don't have the concept of two judgments, let alone one. And then it's a colossal mess. I mean, it's a dirty, horrible mess. It is. It's terrible. But when you work in the type theoretic framework, it's very beautiful. At least I hope you thought so. From Frank's lecture, I caught the end of it, and I know it very well. It's very beautiful. It's very beautiful, but it's a little tricky. You get to see the correct true path. But if you saw the whole tree and then looked at that branch, you would understand the insights that are there. It's a very you can be deceived if somebody just shows you the nice way of doing it. Just, I don't know, looks all right to me. But if you understand, if you see, put it in context, you'll see what is important.
So she asked if the other one was true.
Well, that's what I was showing, the other direction.
Is that also sort of the definition of the IDA data type? Like the fact that it's REPL is AA, right?
Yeah, so the way in which all I'm saying is there's a meta theorem that says what I accomplished with that axiomization of the identity type was to internalize definitional equality. Right. This leads to the following curious situation. Okay, so can I go on? Okay. Yeah, what? Where are you? Say it again. Well, that was definitional equality. Was I using that notation? I can't remember. I'm not even self-conscious.
I think so.
It's all the symbolic execution. That they're definitionally equal. That is, that they're equivalent in the least congruence that contains the inversion principle, that the eliminator inverts the introduction. So that was the symbolic execution. Remember we talked about that. So like you would have first of a pair is equal to the first thing, etc. Okay, that's what I'm doing. Or if you run a recursor on 0, it jumps to the base case, etc. Okay, so that's proof reduction. Okay, it is contained within definitional equivalence.
So they're equivalent as a proof of A, or each of them is a proof of A and they're equivalent?
Say that again, please. It means M and N are proof. If you think of it as proofs, M and N are proofs of A, and they're equivalent proofs in the sense that I defined.
The equivalence is not a proof of A. The equivalence of M and N is not the proof of A.
Their equivalence of M and N is not.
So A is the type of
A is the type of proof. I mean, A is thought of as a proposition is the type of its proofs.
Okay,
So-
I'm just wondering the equivalence is the proof, or whether M is a proof of A and N is a proof of A and they're equivalent.
That's the second thing, right? Okay, and that's what I mean by this being a judgment. Okay, so this is the judgment of definition. This is a judgment. It's not. You see, this is a judgment. This guy here is a proposition or a type. Well, it's a type or a proposition. You could also say it's a family of types or a predicate or a relation, whatever words you would like to use, propositional function. Okay, so those are different things. The distinction between the judgment and the type is extremely important. The conventional treatments of logic don't have any such thing. Okay, you don't see it at all. It's too bad, but this is the right way to do it. Okay, so that's what I'm showing you. Okay, all right. I think it is important to understand these things in terms of, partly to understand how things fit together with other things you may have learned about. That's why I make those remarks. Okay? So, because then I can show you what is different and important here. Okay? So that when you go back and think about it later, you'll hopefully remember that. Okay. So, all right. So you can write down this term. We agree? You can do that as an exercise. This is not hard. Okay? Are you okay with that? All right? I hope you're okay with that. So it's a double induction. It'll be a recursor. You can write down that proof term. So we'll leave that as an exercise. Okay? We'll do that. Okay. Now, unfortunately, here we have the following fact. The type id, let's write it, n arrow n of lambda x, lambda y, x plus y, lambda x, lambda y, y plus x, in fact, is not inhabited. It has no proof. Why? Because they're not definitionally equal. And I'm applying Martin-Löf's theorem. Okay? Because they're not definitionally equal, they're not. They're not. Okay? Because they're not definitionally equal, that is in the least, that symbolic execution sense, because the point is that these are just variables, right? And if you just try to do symbolic execution on the expression x plus y, you're immediately stuck because there's nothing to reduce. The rules for plus will tell us what to do when this is 0 and what to do when it's successor, but it doesn't tell us what to do when it's y, okay? Or here, x. So these things are not definitionally equivalent. Because they're not definitionally equivalent, this type is not inhabited. So to say these functions are not equal, that's a possibly, I hope, surprising and unpleasant state of affairs. Okay?
Is Martin-Löf's theorem an if and only if, or is it just one?
Well, it is for a trivial reason, but the interesting part of the theorem is left to right. And I'm applying the contrapositive, which says if they're not definitionally equal, then it's not inhabited. Yeah. So, yeah. I don't need the other direction. I'm just doing the contrapositive of the direction we stated. Okay. Yeah. So, yep.
Dependent type theory does not refute this either. Dependent type, your system does not refute this either.
Oh, it doesn't refute it. No, it just does. It's not inhabited. I'm telling you, it's not inhabited as a meta-theoretic statement. You will not be able to find a proof of that statement. Why? Because if you were able to find a proof of this statement, then by Martin-Löf's theorem, they would be definitionally equal. And these are not definitionally equal.
Okay, I see that.
Okay, that's the point.
My question is, it does not refute it either.
No, but that's the whole point about constructive type theory. It doesn't postulate some kind of bivalence, that if something fails to be the case, it's necessary. That's not the case. It's just unresolved. There is no proof of this fact. It's not the same as, but it's analogous to like an open problem. If you have an open problem in math, you don't have a proof. You don't know. Okay? So here, by meta-theoretic considerations, I can tell you there is no proof object of that type. Basically, by appealing to a very big theorem, but which I'm suppressing the proof of here. Okay? All right? Yes?
You can change the theory so that you get inhabited.
Oh, you can. Yeah, no, I can. That's what I'm going to do next. Okay. So the point is you get axiomatic freedom here. I'm simply saying it's not inhabited on the basis of what I've got so far. I could, for example, introduce a variable of that type, and I would not be inconsistent. Okay? If I introduce a variable of that type, I wouldn't have an inconsistency because it's not refused. It's simply not inhabited. Okay? So that's the difference. Okay? All right. So this is what I would like to say. Okay. So now the question is, what do you do? First of all, I would like you to feel, I hope you do, this is a very curious situation because it says, thought of as a mapping, as an open term. What we have here is we know that, well, for every x and y, these are the same thing. There's a proof that they're equal. Yet, when you internalize them as elements of the function type, they're no longer equal. That's something very odd, okay, about this situation. You would think it ought to be the case that this gives you that. Okay, but it does not. Okay? And this is what we're looking at is the principle of extensionality. And this is what I would like to discuss. Okay? And then this will lead me to my next thing. Okay. So what I would like to do, so what we're saying here is we're looking at this principle, what I will call, in fact, to be emphatic, unfortunately the word extensionality is grossly overused. So with many different meanings. So let's try I'll call this function extensionality. And what I'm calling function extensionality is not always what people call function extensionality. I'll just warn you. Okay? And I'll explain that remark in a moment. Okay? But the principle of function extensionality would be this. It says, if for every x in A, you have a proof, well, this could depend on x. So let me just write a little x there just to emphasize. This proof could depend on x. If I'm able to prove, and I have some type B, which itself could depend on x, that mx is equal to nx, okay, then there ought to be a proof object called, I'll call it extensionality of P, which is a proof that pi x in A, B, Mn. That is the principle of function extensionality according to my definition. Okay? This is the principle of function extensionality. It says that if you give me a proof, uniformly in x, if you give me a proof that mx is equal to nx for all x, then you should be able to turn that into a proof that the m and n are equal as functions. Okay? So this is not derivable in the type theory that we have so far for the reasons in what I'll call ITT, the thing we have defined so far, in so-called intentional type theory. Okay? So this stands for what is called intentional type theory. That's the thing we've defined so far. Well, why is that not derivable? Because if it were, then then it would be the case that these are equal, but then that would violate Martin-Löf's theorem, so something's wrong. Okay? So it's not the case. Okay? So this is a new principle. Okay? This is something that is not already present in the theory as I've defined it for you. Okay? So this can be a little, it ought to be a little bit surprising. Okay? Now, as an exercise, I will ask you to show that function extensionality is derivable from two things, from two principles. They're called eta and psi. And psi is sometimes erroneously called extensionality and is more reasonably called weak extensionality. So this is also called weak extensionality. Sometimes people call it extensionality. Personally, I find that confusing, and I don't think that's a good idea. Okay, so eta is the principle, so let's call it, let's just think of it as a constant, that says if I have a pi type, and I have m, so let's put this in any context gamma, so m is of type pi x in AB, then m is equal to its so-called eta expansion, which Frank no doubt discussed with you. Now, I'll get to psi in a second. One reason this might hold is it might be that you postulate eta as a principle of definitional equality. You just say this is definitionally equal to that, therefore eta is just an instance of reflexivity. So there's nothing to say. There's nothing in addition. But I didn't include eta as a principle of definitional equality. Why? Well, you have to trust me, okay? Because it's a kludge that works in certain situations, but it doesn't work really. And so I find it better to not even go there, okay? So yes.
The two terms lambda x, lambda y. Can you explain why the two terms are not definitionally equal?
Why it is not what?
The two terms above.
Oh, why are they?
They are not.
No, I didn't actually prove why they're not definitionally equivalent. Okay, but they aren't. I gave you a proof sketch. I said, look at the rules of definition equality. They're all generated from the definitions of the things involved. So x is defined by the recursion equations, x plus 0 equals x, etc. They do not apply here. That's not a proof, but that's the essence of the proof.
Yeah, but
Okay?
they don't apply on. Yeah.
In other words, x and y are just variables. There's nothing to compute. If you were trying to, so to say, do symbolic execution, you're done already on both sides. There's nothing to do. You see what I'm saying? There's no defining equation for plus that will fit the pattern of either of the terms that are there. Now, that's the argument. That is the essence of what is going on. Now, if you want to turn that into a proof, that's a long story also. Okay, and it can be baked into Martin-Lipp's theorem. You can do in the same theorem. You can extract enough information to be able to actually make this argument totally tight. There, I just take that on my authority. Okay, this is the case. Okay, I can't prove everything. I mean, I would do every single lecture for the entire 2 weeks. Okay, and still. Okay, so all right, so that's it.
So what we're trying to do right now is confront our notion of equality, right?
Yeah, we're trying to confront equality. So first thing I'm doing is I'm pointing out to you that the equality we've internalized may not have been the thing you thought it was.
Yeah.
Okay? It's very easy in this kind of situation to accidentally think that something is true that you think ought to be true. Okay.
So if you did just say, okay, I want to add eta to my definitional equality, then that would be a hack that would work for this, but it wouldn't work for.
Well, let me ask you. It would be a hack, but I would like to ask you to consider why specifically it would be a hack. There's a technical way to say what is the problem.
Well, because there's a more general thing that you could do that could account for more stuff.
I think you said it right. Could you say it again?
I said there's a more general thing you could do that could account for more stuff.
Well, yes, that's also true, but that isn't what I had in mind.
Okay.
So what I wanted to point out is if you look at the elim form, okay, suppose I added eta as a constant. What is J supposed to do with eta? See, if you look at the execution rule, J knows how to behave on REFL. What is it supposed to do with eta? No, it's a serious question. I'm teaching you something here, so let me go on with my little story and keep your objection in mind. You have a perfectly valid point, but I want to sort of play it out my way.
Oh, I wasn't really objecting.
What's that?
I wasn't really objecting.
No, I know, but you were onto something. Okay,
Okay.
so I'm gonna say, bear with me.
Okay.
Okay. All right. Okay. So, all right. So we could add definitionally. We could add this in as a constant, but then you have to ask yourself, what is poor J supposed to do when you run it with that constant? Well, there's no good answer to that. Okay? That's an unpleasant problem. And the problem is worse with Xi. So what is the rule for Xi? Xi says this. It says, and watch carefully what I do here. So if I say, if you have a proof P of the identity in B of M and N, not MX, NX, but M and N, then there's a proof, we'll call it Xi of P, which is a proof of the identity at the pi type of lambda x m and lambda x n. This is called Xi or weak extensionality. Okay. So poor J would also be in trouble again if you gave it psi of P as an argument because it doesn't know what to do. And in fact, what would happen is, for those of you who know about these things, the most elementary idea of the progress theorem would fail. You'd have a well-typed program that got stuck because the poor thing, yes? Did I write it down wrong? The P is. Oh, the P can depend on X, certainly, yes. And so can the B and the M and the N. They all could have X in it. Okay? I don't want to write it there. It might look, I don't want to confuse it with that. So notice it's not the same thing as extensionality. Function extensionality is different. Okay? But you can show as an exercise that function extensionality is actually interderivable with psi and eta. If you have psi and you have eta, you have function extensionality. If you have function extensionality, you have psi and eta. Show that they're interderivable. Okay? So we'll say it's interderivable with these two things. This is, in fact, just a classic result from the untyped Lambda calculus, in fact. Okay, what I'm repeating here. Okay? It's basically what I'm doing. But it's worth knowing, and a lot of times people call that extensionality, and my plea is, please don't call that extensionality. Let's call it weak extensionality or psi. Okay? It confuses matters because people use the word extensionality too much. Okay. Okay, so this is a thing. So function extensionality is not already present in the type theory as I've defined it. So now the question is, what do you do? Okay? How do we react to this situation? And now there are various moves we can make. Okay. Now, the first thing I want to get across is this. You might say, I think someone in their question, it sounded to me like they were making the following suggestion. Whether they were or not, I'll pretend they were. Okay, so the suggestion would be chuck it in as a new principle of equality. Add a new rule. Add that as a rule. So one possibility is just add that in as a new rule. Okay? And go about your business. Well, the problem with that is type theory is not an axiomatic theory in the way that you think of like first-order logic. So with like first-order logic and predicate calculus is an axiomatic theory. You get to chuck in whatever axioms you feel like, and the rules of the game are, all you have to do is exhibit a model to show that those axioms are consistent, and then you're happy. Okay? That's the rules of the game. So I can write down any old axioms I want, and then I exhibit a model. Now, there's a problem with that, in a sense, because what are you going to build that model out of? Well, because of Gödel's theorem, the only way you're going to build that model is to assume something even worse than what you're justifying by building that model, and then claim that the thing you did is justified by the even worse thing you did to build the model. Okay? That's a never-ending tail chase. You can't get out of that. Okay? So type theory doesn't work this way. Okay? That's not the way it works. It's not an axiomatic theory. You don't get to just chuck in whatever axioms strike your fancy and then say, oh, well, I have a model of them. That's a pretty lame thing. And the reason is that the way type theory justifies itself is via computation. That's what I said to you in the very first lecture. And this is what I'm getting at here about poor J. Because we need to have, and this is something that I haven't maybe properly stressed here, is we would like to have a canonical forms theorem. If you don't mind, I will put it like this. So an example of what I will call a canonical forms theorem. You would like to know the following kind of fact. You would like to know that, for example, I'll just pick something. If M is of type 2 and it's a closed term, then it's definitionally either equal to true or it's false. I mean, this should make perfect sense, right? I mean, I should hope that the only Booleans are true and false, right? I should hope that there are not 3 Booleans, okay, or some strange thing. Well, so the whole setup of type theory is designed to make canonical forms theorems of this flavor come true. It's extremely important. And the justification for this is essentially the kind of argument that Amal will be telling you about, and that is in Martin-Löf's theorem that I quoted before. There's an argument you can make that says it is indeed the case that if M is of type 2, then it's either equal to true or false. If you throw in an additional axiom like this, it fails. And the reason is you can take a term like J of X of P, and with suitable finagling around, come up with something of type 2. You can do this. Okay? But that thing is irreducible. It's not definitionally reducible. That is, it cannot be simplified because poor J has no idea what to do with this random axiom you chucked in called XP, and you get something which is stuck. So you get a strange beast. You get a closed term that is of type 2, which is neither true nor false. Yes? I'm building my story. Okay, so I'm building my story. Okay? All right, so now moves that one can make. So the first move that I wanted to make is the impulse to just chuck in a new axiom should be resisted, okay? Because you're going to screw up the computational interpretation of type theory on which everything is based. The fact that type theory works so beautifully for all of the wide range of things that it works for really, really, really depends on that, okay? So you can't screw with that. That's like so basic that it's a problem. So just chucking it as an axiom, that's not a good move. That's a desperation move, okay? And we don't really want to do that. Okay, so now there's another thing, and I was specifically asked to, or enjoined to, yes? That's right, exactly.
But you didn't say how equality is defined as intentional activity.
Yeah, I gave you a definitional equality, that's what I said. Definitional equality. Okay, so if I take intentional type theory and I have, which is based on definitional equality in the way I defined it, I internalize it with the identity type, the function extensionality is not a derivable. It's not present in that rule. One can prove this, but but you need a big theorem to prove that. Okay. Throwing in an axiom is a desperation maneuver. We don't want to do that. There's another approach. There are several other approaches that I'm going to discuss. There are three, okay, that I'm going to discuss. One is to pass to what is called extensional type theory. Unfortunately, this is another one of those uses of the word extensional, and it's all related. They're all related somehow, but they're not exactly technically the same, okay? So if what we had so far is ITT, that's what we've done so far, there's another way to justify, there's another form of type theory one can give which avoids all of these problems, and it's called extensional type theory. An example of this is the New Pearl type theory, is a particular extensional type theory, and Bob Consul will be talking about that shortly, okay? So what is extensional type theory? Extensional type theory is based on the following these following two additional rules. So what we do is we replace, I'll call it like that, identity elim with the following two rules. So we get rid of J because it will, with the following rules. Let's write them. We'll get rid of J because it will turn out that once I've made this move, J is derivable. Since J is derivable, all the principles I told you before about reflexivity and symmetry, transitivity, substitutivity will all be derivable because they all use J. So, but what I'm going to do is I'm going to get rid of J because it will be definable once I give you these two rules. And the two rules are called equality of reflection. Okay, so IDA reflection and uniqueness of identity proofs. And this point, UIP, is related to the homotopy interpretation I described to you before, and I'll get back to that. So the equality reflection principle says the following thing. If you have a proof that M and N are a proof of the identity of M and N, then M and N are equal. Now, I could write it like this if that's the notation I've been using. But in the presence of this rule, people tend to write it like that. I'm sorry, but I'm also trying to guide you through the literature, okay, for a reason. So the point is, this is the judgmental equality. Until now, it has been definitional equality, which is generated by computation. I'm now going to change the meaning of judgmental equality, okay, to include the possibility of something that was proved, for example, by induction. Okay? So now if we go back to this example that's written here, okay, in extensional type theory, the fact that this proof term exists tells us, I need to find a place to write it, let's do it here. In extensional type theory, in ETT, this means that on the basis of those same variables, x plus y is equal to y plus x judgmentally. You could write triple bar if you want. I changed the notation to emphasize that I'm working in extensional type theory. That's the reason. Okay? So those are equal. But everything respects equality, the judgment of equality. So that will tell us in particular that it will follow as a corollary, all right, that lambda x, lambda y, x plus y will be equal to lambda x, lambda y, y plus x judgmentally, and therefore by reflexivity there will be a term inhabiting the identity type n arrow, this should say n arrow n arrow n, and therefore since those are equal, then this identity type will be inhabited. Because they're equal, and everything respects equality. Right? So since everything respects equality, so the proof object turns into a judgment of equality. This judgment of equality, equality is a congruence, so I can replace equals by equals anywhere. And since those two things are equal, the type with this on the left and this on the right is the same type as the one with this on the left and on the right, and therefore it's inhabited by reflexivity. So this will be an instance of REFL. And you will get, therefore, there will be an inhabited term at that type. In other words, function extensionality is derivable, okay, in ETT. Okay? So you'll be able to do that. So this rule is called identity reflection. The other rule is called uniqueness of identity proofs. It says if you have any proof of A, IDA, MN, then P must actually be reflexivity of M in the type IDA, MN. This is called UIP, or I would call it discreteness in a way. It's homotopy discreteness. I'll explain that in a second. Okay? These two things correspond. Okay, yeah, I don't want to get ahead of myself. First, let's this digest. Okay? Take these two rules. And now you can show as an exercise, okay, so as an exercise, you can show that fun x, in ETT, you can fun x is derivable and j is derivable. You can do 1 and 2. That is, when you're working in extensional type theory, you can already write down a proof term for fun x. You can already write down a proof term for j. Since you can write down a proof term for j, as I remarked earlier, then you can carry out the proofs that equality is symmetric, intransitive, and substitutive, and da-da-da-da-da-da. You have respect everything, because all those things only depended on j. Okay? So this is called extensional type theory. Another way to describe this, which is a little more modern, is to call this, you're not going to like this, I'll call it set theory. And what I mean by this is, I'll write it like this, homotopy set theory. This is the right way to think about it. The reason is that look at what this is telling you. Uniqueness of identity proofs tells us that homotopically, the type A thought of as a space is discrete in the following sense, that the only paths, if you have elements of A, so here's A, you have various elements of A floating around, okay? The only paths that exist are the paths between these and themselves. There are no other paths between points in the space. That's said to be homotopically discrete. And from a homotopy theoretic point of view, that is said to be a set. Okay? A set is a homotopically discrete space. That's the terminology. It doesn't mean the same thing as set theory and axiomatic set theory. I'm sorry, but the homotopy theorists use the terminology something is a set to mean, or a homotopy set, or an H set. Sometimes people will say H set. An H set is one which is homotopically discrete. The only paths in the space are reflexivities. It's completely degenerate in a certain way. There are no interesting paths. There's nothing like this. That can't exist. There are no interesting paths. I'm going to show you very shortly situations where I want non-discrete spaces. That leads to higher dimensional type theory. I'll get to that in a minute. So another way of saying it is it's homotopically a set or homotopically discrete, or another terminology that people will use is they'll say it's one-dimensional. So the new Pearl type theory, I would now say, in retrospect, is a set theory because it commits to the idea that all types are homotopically discrete. Okay? That's the idea. All right? So in new Pearl type theory, you can correctly think of types as sets in exactly the sense that the elements are given discretely. Okay? There's no cohesion in such spaces, or the cohesion is rather degenerate. It's very granular. That's the way of saying it. It's a granular space in which you just have isolated points everywhere. Okay? And there's no idea of cohesion. We're going to talk about cohesion in a minute. Yep.
Discreteness property that allows you to show canonical forms?
It's related to that, yes, because the proof of canonicity in new Pearl is an argument of a kind similar to the one I quoted from Martin Luther. It's not the same thing, but the new Pearl semantics goes through a lot of trouble. And here, let's watch what's happening. If I think of this as a groupoid of a particular structure, it's a groupoid, okay, in which all I have is an equivalence relation. So what happens is in new Pearl, because the idea, in other words, there's no evidence. I have a bare equivalence relation where there's no non-trivial evidence of the relationship between points, because it's always reflexivity. Okay? So what's going on here is we're looking at types as pairs, partial equivalence relations. And what you do in new Pearl is you prove a canonical forms theorem by showing that types can be interpreted as partial equivalence relations, or really homotopically discrete spaces, that they're sets. So you interpret them as sets, and everything is partitioned up like this, and there's no cohesion, and then you get a canonical forms theorem.
But in two-dimensional type theory, you can't do that.
No, in higher dimensional type theory, that's not the case. The pairs don't work. Groupoids are a generalization of pairs. Remember, a groupoid can be thought of as an equivalence relation with evidence. You don't merely say X is equivalent to Y. You say there's a reason why, and there can be multiple reasons why. So not only can there be more spaces, but there can be many paths between the same 2 points because there can be different reasons why they're related. Okay, but with pairs, no, that can't happen. Okay, so it's a degenerate. So from the modern perspective, which is like the last year, approximately, we suddenly realized, or I suddenly realized, that new Pearl all these years, what it's really doing is set theory in this terminology of sets, that is, in the sense of being homotopically discrete. Yes?
Set theory because of the discreteness rule?
I can't.
You say it's set theory because of the discreteness rule.
Because of the discreteness property.
But couldn't that rule be added to intentional type theory without the extensionality?
I didn't quite catch that.
Couldn't that rule, uniqueness
UID alone?
Be added to intentional?
No, you can't do that. I should have pointed out, this UIP rule only makes sense in the presence of this rule. And the reason is, in principle, P is a path from M to N. But if you're claiming it's equal to reflexivity, then you're saying it's a self-loop, that M and N must in fact be equal. And so the only way to know that is to use the identity reflection. So these two things go together. We can't just do this one. Okay? If you didn't have this around, this rule would not make type sense, because the type of REFL M is IDMM. The type of P is IDMN. Where it doesn't make sense to talk about it being REFL. Okay? Only if it's you have extension with this reflection. So these two go together. It's quite important. Yes?
Don't you have uniqueness for that groups in EGA, but not the ID reflection? In EGA, there you have uniqueness in identity groups, right?
Well, there's a switch, I believe, in which you can have it or not have it.
Well, no, it's like in Coq as well. There's a version of it where instead of IDA-MN, you say IDA-M, and then you in the middle of the type there's uses substitution from the equality.
It's a little hard for me to handle this discussion here in front of everyone, especially since I have a lot of other things to do.
Okay.
So let's come back to that a little bit later.
Sure.
Okay? I don't know specifically about whatever AGDA has done, but anyway, I do want to make this point. called extensional type theory. I would now call it, kind of set theory. Unfortunately, that the words get into trouble. So it's a theory of homotopy sets. Okay. So sorry. Yes.
So in intentional type theory, the definitional equality is decidable, but here it is not.
Yes.
Right.
That's true.
Okay.
I haven't proved that. And I don't care.
But isn't one of the main points in court of proof that proof checking?
Yes, I know. We can have this argument offline. Okay? To me, that's a big red herring. It's irrelevant to the practice of mechanization of mathematics. Totally irrelevant. That is we'll argue it offline. Okay? So yes, it's quite true, but anyway, I don't care. Okay, there's another thing I would like to tell you about, which is related to this. There are two things I want to do. At what time am I supposed to finish? Where's Bentley? There.
Nominally pretty soon, but
Okay.
officially pretty soon, but I think a lot of people are interested in what you're doing.
Okay, so let me see what I can do now. Okay. There's another move that people have made to deal with the issue of extensionality that also doesn't extend, it does not extend, it's also low dimensional. It's for the purpose of doing a set theory, but it does it in a different way. So let me explain that. So I promised various people offline that I would mention these things, so that's why I'm bringing them up. Okay, so, all right, so I've discharged my obligation to distinguish those two. Okay, now there's something else called OTT. You'll like that. Which I don't know about this term. I don't know why it's called this really, but it's called observational type theory. I don't know what I would call it, but there's an interesting and useful idea here. It's another attempt at dealing with the idea that types are sets. So they're going to be homotopically discrete, but it's done in a different way. And the idea is this: is you define ID of A. So you now get rid of everything I've said about identity and start over. Okay? And what you do is you define ID of A by induction in the structure of A. And the critical thing is the following fact. That what you do is you say the identity at pi x in AB, let's say Mn, is by definition the product over x in A of identity B, mx and nx. It is extensionality. And you do other moves for sigma and da-da-da-da, they're similar, but this is where the action is in this discussion, so let me focus on this, okay? And then you define REFL, because now I'm defining type theory all over again. So I define REFL for pi x in AB of M is defined to be lambda x in A, okay? REFL of mx, if I'm not mistaken. REFL of B, mx, it should be. And if you do this, you can validate all of the rules of type theory that I gave you before. Okay? So in other words, so here's my identity for a particular A, and I'm going to do this for all the A's by induction in the structure of A. When I define what the identity is, I define what REFL is. So what I do is I say reflexivity is not some primitive token, right? It is extensionality. But you'll notice if you play this out and go by induction in the structure of the type, you're retaining the principle that there's only one path between two elements of the type. You are still homotopically discrete. Because this is the unique reflexivity at B, and then this is the unique function that that gives you reflexivity every time. So you end up also with a set theory, but you get to it by a different route. And that's the essential idea of OTT. Okay, there's more could be said, but it's basically the idea. Okay? Yes?
What exactly do you mean by pi over x in a IDD?
Well, see, I'm defining ID a family of types by induction of the structure of the type. So this is a constituent type of pi x and AB. So I can assume IDB is already defined, and then I extend it to pi x and AB in this manner. And with sigma, you do something similar. With sigma, you say sigma x and AB. I'm going to wing this, and I'll probably get it wrong, but it's essentially, it ends up being sigma. In fact, it ends up being a cross, if I'm not mistaken. That's where I'm going to screw it up. I think you end up saying it's IDA first of n, maybe, cross ID substitute first of m for x in B, second of m. I think I didn't prepare this, but I think that's correct. Okay. I've done similar things in my studies of singleton kinds and so on. If you look at the papers that we wrote about that, we invented this notion independently. It's a similar idea. But for our purposes of the discussion, that's where the action is.
I think the question was the position of x and a under the pi rather than to the right pi.
Why are we using big pi?
So the position of x.
Where are you pointing here?
On the pi.
Right. Big pi on the board with the x under it.
Yeah. What do you mean, why are you using it? What else are you going to do?
all of your bindings are meant to the
Yeah,
right
you bring
pi.
it notationally different than normal.
Yeah. Is it significant that the x is under the pi instead of to the right of it?
Oh, no. This is a big pi type, okay? So in other words, the identity at a pi type, in other words, I define an infinite family of types, id sub a, for each choice of a. And I get to define, in other words, I don't just say there's one family of types, how do I say this? I care about the a. Whatever the choice of A is, depending on what A is, it is defined to be a different type. Because when A is a pi, it's that type. When A is a sigma, it's that type. Okay? There's no fixed identity at that type. You just say it's defined inductively on the structure of the type. And you can argue that this is going down. That's the idea. Okay? So that's the that's the essence of the idea. And if you work in OTT, then you get a lot of the benefits of extensionality. You no longer have this pathology. So this type now becomes inhabited. Okay? So as a corollary, if we take id n arrow n, remember arrow is an instance of pi, lambda x, lambda y, x plus y, lambda x, lambda y, y plus x, is inhabited now. And it's inhabited by the very obvious thing. It's inhabited by reflexivity. It's inhabited by reflexivity defined this way. It's inhabited by lambda x in A, lambda y, n, lambda x in n, lambda y in n, refl in n of whatever it's supposed to be, x plus y and y plus x. That's what's going to happen. Okay? No, in fact, what's going to go here, that's what it'll wind up being, I think. But it's inhabited. You'll be able to show that that type is inhabited. Yes?
Are you going to say what x is a function of extensionality?
Aren't they what?
Are those two things a function of extensionality?
By definition, if you say that equality, what you're doing is you're saying equality at a function type is extensional equality, function extensionality.
Observational type theory rather than extensional type theory?
Could you say that? This is different from extensional type theory. It's different from intensional type. Because extensional type theory is defined in that way that I described over there, with equality reflection and UIP. With equality reflection UIP, function extensionality, the board is obscured, is derivable by set that as an exercise. Okay, that's extensional type theory. There's another thing called OGT. No, I doubt it. But I'd have to think. I have to, whether those two theories are equivalent in all respects, I am going
Does one
And
subsume
easy
the other?
is the other.
Well, if anything, OGT is contained in EGT, that I'm sure. Okay, EGT is much more powerful for sure, for certain, but I have to think carefully, and I don't know, I'm not going to commit to an answer about that because I'm not positive that this answer. Well, if I knew that, then I would be able to answer your question. I wasn't prepared. I didn't think about that last night to remember, so I have to think. Well, I have to think about this one. I'm sorry, that's the best I can do. Yes, okay. Yes.
On the upper bar, the group term for the fact that we've shown is not just red, it's two user proximity. So is it not this group term that we should have on the right to prove the equality of the two?
Yes, it might be. That's what I was supposed to do.
Okay.
Yeah,
Because this one looks very simple, a bit similar.
Yeah. I have to think whether this may not be the right group object, but it's definitely inhabitable. Okay, I'm sure this may or may not be the right group object. That was what you're asking. I have to check that offhand. Okay. You're going to have to incorporate that recursion group, yeah. But what it'll do is when you run it on the arguments, it will compute the reflexivity, and that's what I want. That's the thing I want to get at. Okay. So I have more to say. So are there questions on this? Okay, good. All right. Now I want to show you something.
Okay, so these are like the known low-dimensional approaches to dealing with extensionality. There's a higher dimensional way to deal with extensionality that I will approach a little bit obliquely. I'm going to bring up something else in order to get to where I need to get you. Okay? All right, so let's do this briefly. So the fourth move you can make is you can just say, I'm going to live with it. Well, that's not a very, I mean, that's one thing that people do. But I want to, let me correct myself. I take that back. Let me correct myself and say, let me correct myself there. I'll take that back. Basically, I don't have enough time to say the thing that I really need to say. There's another way to get at the issue of extensionality, which is via a roundabout route. It looks roundabout. It's via a principle called, well, there's two possible principles. One are what are called higher inductive types, and the other is called the principle of univalence. These two principles, either one of them, are another route to around the problem of extensionality that I would like to tell you about. But I can't do it in 5 minutes. Okay, so so what I want to do is I want to give you a flavor of what that route looks like. Okay, and then we'll have to decide what we're going to do, and because we should break for lunch. Yes, is that good? Okay. So I need another half an hour, to be honest, okay, to do this, okay, properly, because I need to then introduce either higher inductive types or universes, and I have to do, and that will take a little while, okay. So let me instead slightly change the subject, and trust me that this is on the vector, this is on the right direction to doing that story, and if we eventually do it, I will, okay. And here is the idea. Let's revisit the groupoid structure. The groupoid structure of identity types in ITT. Let's look at it. We'll go back to the first thing in ITT. So what I said to you before is that we have identity or reflexivity. So we can think of this, in fact, I'll start writing it like this. We can think of that as being a path in A from X to X. Or you could write that as a self-loop. And we say if you have a path from in A from X to Y, then its converse, if you will, is a path in A from Y to X. So you were able to define that. And you were able to define composition Q after P, which is a path in A from X to Y. If P is a path, no, let's call it X to Z, how about? All right. If P is a path from Y to Z, or what am I supposed to say? X to Y, A, and Y to Z, or did I do it backward? Did I do it backward? Somebody's mumbling what? Yeah, okay, good. Okay, so we first looked at this. We were looking at the groupoid structure. So you're able to define these things. So in the beginning of this lecture, I gave you a hint about doing that. Last time I showed you how to do that. That we have for free by definition. Okay, so we have that structure. So the thing that I want you to do now is if you look at the algebraic structure, what makes it a groupoid, and I hinted at this last time. So the idea is that we should have something like the laws for a category, which says P after the identity is P, and the identity after P is P, and you have to write in the right types to make that work. And we have an associativity after R. And now the equals, this is all the issue, okay? So P after Q after R. Write in the correct types, you have to do that. And the inverses in some sense of equality. Okay, so they look like this. So those would be the equational laws you would expect to hold to be a groupoid. These are the laws you need for a category, which, tongue-in-cheek, you could call it a monoidoid. And this is what makes it a groupoid, which is a category in which all maps are iso. Or another way of saying it is, yeah, okay, that's what we'll say here. Okay? Okay, so that's the, the additional line. So those are the axioms. The question is, in what sense do these equations hold true in ITT? And the answer is, okay, I'll just go to this. So if we had a strict groupoid, then these would be definitional equivalences. And that is not the case, okay? You will not be able to prove, okay, that these hold as definitional equalities in ITT. You will not be able to do that. So that is not the case. But in a weak sense, a weak groupoid, they hold up to higher identities. And that's the interesting case, because this is the higher dimension. And the easiest way to do this is to give a description of what is going on here, give a picture of what is going on here, which I alluded to last time. What we have is we're looking at equations, just like fuzzing out a little bit. We're looking at equations between paths. So we have a space, and we have some endpoints like x, and we have y. And there are various paths from x to y that can be made up out of the material we have here. Maybe this is a reassociation, associated one way, associated the other because there's an intermediate, or whatever. But the point is there are different paths from x to y. So the question is, in what sense are these things equal? So let us say that this is supposed to be an instance of one of these axioms. So this map may be P composed with P inverse, and this is P composed with, or an associativity, or whatever it may be. Let's suppose that this path P and this path Q are supposed to be equal. Well, they're not going to work out in type theory to be definitional equalities. But what you can do is you can find that you can show that these equations hold true up to higher homotopy. And what does that mean? What it means is that you think of a two-dimension, you add another dimension. And what you do is you think of these things as being edges, okay, of some kind of a geometric figure, and there's a surface that connects them. Think of it like cellophane paper that is stretched between these two edges, okay? And that cellophane paper represents an equivalence between these two proofs, or a homotopy of paths. So this thing, alpha, is a homotopy of paths. That is the cell structure that we have here, the cellophane that connects these things. It represents the deformability of P into Q, because I can glide that path along. I can contract the cellophane by like heating it up or something and making it shrink, and I can shrink P into Q. And that shrinkability, or contractibility as the terminology goes, the contractibility amounts to a proof of that they're equal in the sense of a higher homotopy, in the sense of a deformation. Okay, there's a deformation of P into Q that goes along that surface. If you look at that type theoretically, what is alpha? What is that deformation? Well, it's going to be a term whose type is of iterated identity type. Because if this is all happening within A, then you're taking the type of identities, the type of paths from X to Y, and you're looking at a path between the paths P and Q, which is a homotopy of paths. So you get this characteristic structure of an iterated identity type. It's an identity, it's a path between paths within the space A, or a proof of the equality of the proofs of equality of the elements X and Y in A. Okay? So that's the flavor of how this goes. And then this extends to arbitrary higher dimension. Okay? So what you can prove, and you can do this as an exercise, is you can show that these laws in fact hold. So the exercise is that they hold in ITT up to higher homotopy. So I'll call it up to higher homotopy. In other words, you'll be able to exhibit identity alphas, which is an element of this identity type, which witnesses the required equations. Those proofs will involve further uses of trans and sim and subst and resp and stuff, which will themselves be justified by an even higher identity. Okay? All the way to infinity. And that gives you the structure of what is called an infinity groupoid. And an infinity groupoid is the place where people want to do homotopy type theory. Homotopy theory, that's where all the action is. Okay? And type theory, it turns out, for this reason that I'm sketching, and I think Steve will go into more details, to be a very natural and expressive language for discussing infinity groupoids. That's the nutshell of it. Yeah?
Quality statements?
Well, don't make me do it.
Just a statement of it.
Okay, let's leave it for a problem session or something.
I'm looking for an example like this alpha of it is.
Yeah. I don't want to try to write it in front of the board. I didn't write it down in my notebook already, so I'll have to invent it. It'll take me 10 minutes.
Not the proof, just the statement?
Say again?
Not the proof, just the statement?
The statement. Well, the statement would be, you have to look. So if you pick one of these equations, so I'm going to want to find an element of the identity type in A between, these are paths from X to Y for some X and Y. I have to figure out what those are by giving the types to these that they have to be. So that one is probably, it's going to be X to Y between P and P composed with identity. And you're going to exhibit a term of that type. Now, don't ask me to program in front of you because then it's going to take me, I'm going to screw it all up. I have to write these down in advance, otherwise I won't be able to do this board with you. It'll just be confusing. Okay, so type theory ends up being a natural language for talking about these structures.
I need your reaction to the infinite nature segment of this.
Yeah.
It reminds me of what you dismissed earlier about making a complicated model and making a more complicated model to justify the previous one.
I'm not constructing a model. I'm trying to exhibit the structure of the type theory. And the structure has the structure of an infinity groupoid in the sense that the groupoid laws hold up to higher identities. And if you iterate that, if you make no bound on the iteration of that, if you're allowed to iterate with the identity, then you get the structure of what's called, sometimes it's called a Wiesenmaker groupoid. Okay? And that's the structure that we have. I'm just telling you, this is present in ITT. It's right there in front of you. I didn't add anything. I didn't axiommatize anything. I didn't chuck in anything. Okay? I just am pointing out to you that this structure exists. Okay? Now, there's some interesting uses of this kind of structure which I want to close with, which one of these is the idea of inductive types. And Steve will tell you a lot about higher inductive types. Called higher inductive types. What's really slick about higher inductive types is they generalize inductive types to higher dimensions, and in the process they generalize ideas of like quotienting en passant. So the simplest example is what is called the unit interval, which is usually drawn like this. You have
if you think of this as being on the real line, it's the segment between 0 and 1. Okay? So we'll call that's the unit interval, right? Usually what people call that, right? And this is to be thought of as in the real line, right? That's what people usually do for the unit interval. You can axiomatize this as an abstract type rather than as a concrete type. There's an interesting phenomenon in the usual treatments of homotopy theory. People work at the assembly language level all the time. They code stuff up in terms of real numbers and continuous functions on, let's say, the reals or complex numbers, when they really, so to say, should be working using data abstraction like good functional programmers. And if you do, then here's what you get, is you get the following inductive type. I have a type that has two generators, 0 and 1. Okay, so those are the endpoints. And the only thing I care about the unit interval, when you're talking about topology, you're talking about deformations of spaces. Notions of length and angle don't exist. There's no idea of distance. There's no idea of angle, okay? So the only thing that matters is that these are connected. So what you have is what is called the segment, I'll call that the segment, which connects in the interval 0 and 1. So a way of thinking about this is that what I've done is I've taken a type and quotiented it by demanding that 0 be equal to 1. The segment is the type with 2 points that are both equal. It seems strange at first, but it's actually quite true. And then you can start talking about things like the circle, and there are different ways to talk about the circle, which would be depicted like this, okay? And what it is I have a base point in S1, and then I have the loop, okay, which is a path in the circle from the base point to itself. That's an example. And that's a higher inductive definition of the idea of a circle. Okay, that's what a circle is, topologically speaking. It has a distinguished point, and you can go around it. Okay, and that's what it's used for. Someone said something? No. Okay, and you can go around it. And you can go through and you can look at all of the higher spheres. I won't write them down here. You can use a construction called suspension, if some of you know about this. There's a way to go from n to n plus 1 in a systematic way. And there's a nice construction of all these geometric objects. And now you start doing functional programming with these geometric objects in a very nice way using abstract types. And you occupy this incredibly beautiful little world. And it's all just functional programming. Okay, this is what is really, really nice about it. And I will mention a surprising thing to you, which will round out today's lecture. The existence of the segment, see if you can intuit why this might be the case. In the presence of the unit interval, the interval, you could say, implies function extensionality. That might seem very surprising at first, but once you get used to these ideas, you will realize that it's not. It's not surprising at all. Okay? If you have the interval defined this way, you can use the interval, and I haven't explained what the elim form is yet, so that's the problem that I have to do, is show you how you program with an inductive type. But what you do is you do case analysis on the two endpoints, and you also have a higher case analysis representing the fact that the endpoints are joined. Okay, so you have a kind of higher dimensional primitive recursion principle. If you have that with the interval, Steve will show you, then you can derive function extensionality from that. Okay, just from the interval. It's a very simple functional program to do this. So as soon as you have these higher dimensional objects, you get function extensionality. So that's one reason why all of this is really about how to deal with function extensionality, because once I develop this idea of higher homotopies, that gives me higher inductive types. When I have higher inductive types, in particular, I have the unit interval, and once I have the unit interval, I have function extensionality. So it's a funny route, but that's the reason why I had to pause there and get my bearings, because it's a bit complicated.
All is in the, you say this is all expressible in the initial intentional type theory.
Yes.
Do you get a principle of substituting equals for equals when you use all of this?
Yeah, because I showed you how to derive substitution of equals for equals from J. And J is present in intentional type theory. So the point, though, that I want to mention is you notice that this segment is not reflexivity. But I don't have uniqueness of identity proofs or anything like that. That's all gone out the window now. I'm really in the higher dimensional case. So these geometric objects only exist by taking advantage of higher dimensionality, of having non-trivial elements of these identity types. Now there's another story involving universes that I don't have time to tell you right now. I would like to tell you, maybe I don't know, maybe we can squeeze in another lecture, I'm not sure. I would like to tell you about universes in univalence and how that plays into all of this discussion. That would really finish what I wanted to do, but this is a reasonable breaking point for lunch. So that's it for now. Thanks.